What's wrong, little Jimmy?
I have to graph sine of x squared, but I don't have my calculator.
Well, gee willikers, I actually know just the thing. It's called a Taylor series.
So first, we start with the function f of x equals the sine of x. Next, we have to take the first derivative of f of x equals sine of x, and we get f prime of x equals cosine of x. Next, we take the second derivative, f double prime of x equals negative sine of x. Then we take the third derivative of x, and we get the third derivative of f with respect to x equals negative cosine of x. So, from here, we evaluate each of these at x equals c. In this case, c equals 0. So, at f of x equals sine of x equals 0, f of 0 equals 0. At f prime of x equals cosine of x, f prime of 0 equals 1. And with f double prime of 0 equals 0. Then we go to f triple prime of x, and f triple prime of 0 equals negative cosine of 0, which is negative 1. So now, Jimmy, we'll use the definition of a Taylor series centered around point C to determine the series formula for sine of x. Notice, however, we'll be using a special case of the Taylor series called Maclaurin series centered around c equals 0. So now, using that formula, we have f of x equals sine of x equals f of 0 plus f prime of 0 times x minus c to the first over 1 factorial plus f double prime of 0 times x minus c squared over 2 factorial plus the third derivative of f at 0 times x minus c to the third over 3 factorial. So now when we substitute, we get sine of x equals sine of 0, which we found earlier was 0, plus f prime of 0, which we found earlier was 1, times x minus c, which is 0, to the first, over 1 factorial, which is 1, plus f double prime of 0, which we found earlier was 0, times x minus c, which is 0, squared over 2 factorial, which is 2, plus f triple prime of 0, which we found earlier was negative 1, times x minus c, which is 0, cubed over 3 factorial, which in this case is 6. So when we simplify, we get sine of x equals x minus x cubed over 3 plus ellipses, the nth derivative of 0 times x to the n over n factorial. Now, if we expand that out a little bit, we get sine of x equals x minus x cubed over 3 plus x to the 5th over 5 factorial, 3 factorial, minus x to the 7th over 7 factorial, plus x to the 9th over 9 factorial, ellipses, plus x to the n over n factorial, plus or minus that. So let's see if we can find a pattern here. If you notice, the first thing we need to do for our series is identify an alternator, because each term switches itself up. So we're going to write the sum to infinity of n equals, we don't know yet, negative 1 to the n. Now, if we look, the numerator is getting multiplied by x squared each time. So for that, we're going to have an x squared to the n. Now, what we also see is that in the denominator, we have factorials, and these factorials are corresponding to that n term. So, we're going to go over n factorial. But now, we look at the first term, and we notice the first term, we have to have a positive sign, which means this n has to be even, or 0. But when you look, when n is 0 here, you have x to the 0, which is 1. So instead what we're going to do is we're going to rewrite this as the sum from n equals 0 to infinity of negative 1 to the n, and instead of writing x to the x squared to the n, we're going to go ahead and simplify that out to x to the 2n, and we're going to go ahead and tack on a 1 at the end, because that way when n is 0, x is still going to be to the first power. So we always have our x as our first term. And then we're going to drop back over, and we're going to have 2n plus 1 factorial. Our denominator here is the same as our exponent. So now, if we go back to our original function, we have the sine of x equals the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1 quantity factorial. Now what you may be wondering is, well, why did I do all this work to find sine of x when what I really want is sine of x squared? Well, it's simple. Because of the nature of Taylor-Maclaurin series, we can actually go ahead and substitute in x squared for every value of x that we have in our above equation. So what we have now is the sine of x squared equals the sum as n goes from 0 to infinity of negative 1 to the n, and then right here we have x squared to 2n plus 1 over 2n plus 1 factorial. So when we simplify that out, we come down here with sine of x squared equals the sum from n goes from 0 to infinity of negative 1 to the n times x to the 4n plus 2 all over 2n plus 1 factorial. Now, the same method can be used for any other function of x as long as it is differentiable.
Like laughing.
What, do I have to do everything for you?